It's 2 hours UTC, and here we are again with Astronomy Daily Live. So, hey everybody, nice to see everyone again. Hope you had a great day, a great evening. Everything's going well here too. So yeah, let's sit back, have a think, have a talk about some astronomical things tonight. Hope everybody's doing well. Just configuring. Got to get over here and pop my chat out before I freeze the machine. Drives me crazy. For some reason, the really only live streams, like completely freeze my Linux machine. I have absolutely no idea why. Not a clue why. Drives me insane. So instead, I watch the live thing over on my smartphone over here. I'm gonna get that started. Hope everybody's doing good. It is officially spring. The equinox passed with with a little bit of fanfare, and the sun moves on. And I actually realized um, that the vernal equinox is not only the point in time where the sun is located at a declination of zero, but it's also uh, a right ascension of zero. So this is we've got to define uh, beginnings of things. So this sort of that position um, in the sky defines sort of our 0 0 point, 0 hours right ascension and 0 hours declination. And when the sun crosses that point, when the center of the sun, right, the exact center of the sun crosses that point, we say that it is the vernal equinox. So yeah, that happened yesterday. Old news. Old news. Old news. So yeah, hope everybody's doing good. This is Astronomy Daily Live. This is just a casual, fun get together of friends every single day. Sit around, think astronomy, talk astronomy for an hour or so. Now, this is for everybody. So whether you're new, whether you're an amateur, whether you have a telescope or not, whether you have binoculars or not, whether you're a pro, you are welcome here for sure. Like to have everybody in here, as many as we possibly can. I'm definitely trying, to grow this crowd. So, you know, um, if you're seeing this not live but recorded, and you haven't subscribed yet, make sure to subscribe. You can hit the thumbs up or the thumbs down, or maybe a sideways thumb. If you can find that option, let me know, because that's an interesting one. Um, there's some information down in the description in terms of links and ways of getting a hold of me. If you want to be on the panel, right, on the Google Hangout, this is called a Google Hangout. Okay, this is not a Google monologue. Um, but if you want to be a panelist down here, I think this allows for up to like 10 panelists or so. Throw me an email at cosmiclettuce@gmail.com, and when the show goes live, I can send you a link to the live stream, and you can pop on here, and we can shoot the breeze. We can talk astronomy. We can talk dark skies. We can talk anything, anything at all. So I've got my regular uh, um, hydrogen hydroxide tonight. Just the regular old standby. Always works well. Cheers. So glad you could stop in. As I said, this is for everyone, and hopefully it's a little bit of fun, a little bit of education, um, uh, just fun, casual get together, really, really loose. No, no real topics coming in, but I've always got some topics right back here in my back pocket. So if need be, it's pretty easy to pull those out, and yeah, think and talk astronomy. Over, just on and on and on. There's always things going on. There's always new things. There's always old stuff. It's pretty amazing. It's pretty amazing science. So this show is also about science and the process of science, and in that it's a science is a process fractal. So what that means is that the outputs of of this process sort of get fed back in, and so it's sort of like a feedback loop. It just goes on and on and on and on and on, and that's what science is all about, right? It's it's going through this process where at the end of one cycle, you take everything that you produced and you feed it right back in. And yeah, you get a lot out of it that way, I think. I hope. I do, at least. Cheers. So I hope everybody's able to take a look at the planet Mercury. It's still up in the western sky. If you look oh, maybe about a half an hour after sunset or so, and look almost due west, you will see a bright white star, and that is most likely, probably, the planet Venus. But just to the right of Venus, maybe a couple of um, fingers extended at arm's length out, a couple of fingers over to the right, you will see another star, much fainter, maybe even colored, right? Maybe a little orangish red. Yeah, something like that. Well, that is the planet Mercury, and it's not entirely rare to see Mercury. It goes around the sun every 88 days. So what that means is that every 44 days it 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 goes furthest out from the sun, and then 44 days later it's on the other side of the sun, being as far away as it is again. 44 days later it rotates back around, and so every 44 days Mercury is extending relatively far from the sun. I want to say it's about 28 degrees or so. So that's not really far away from the sun. You're not going to see Mercury at midnight, right? You're not really even going to see Mercury 2 hours after sunset. You'll never really see Mercury in a dark sky uh, anytime past astronomical twilight, which usually takes about an hour and a half. Astronomical twilight is defined as when the sun is 18 degrees or more below um, the horizon. So it it uh, it takes about an hour and a half for the sun to set that far, um, and so it takes about that same amount of time for Mercury to set. So yeah, you never really get to see Mercury, the planet Mercury, in a totally dark sky, because it's always either running right ahead of the sun or it's chasing the sun, at least from our perspective, right? So yeah, it's it's not incredibly rare to see Mercury. For some reason, sometimes people get more excited than um, than other times. I'm not exactly sure why. I think it's all very, very exciting and very, very awesome. Why limit? Why limit myself to being excited only once every 44 days or 88 days, whatever it is? That's ridiculous, ridiculous. So anyway, go out and take a look. As I said, about a half an hour after sunset, you should be able to look west and definitely be able to see Venus. It's that big, big, bright white one out there to the west. But right next to it, fainter, quite a bit fainter. You're going to have to work a little bit. A pair of binoculars might help a little bit, not necessary. Um, it'll help a little bit. You, you might be able to catch it sooner. Maybe 25 minutes after sunset or 20 minutes after sunset or so. Might be able to catch it in a pair of binoculars. It'll be up a little higher, of course. Um, but yeah, take a look at that. It's always very, very cool. In fact, uh, we're going to be getting into a situation relatively soon. I probably need to check this out before I just make these wild speculations and stuff. But Jupiter and Mars and Saturn are getting closer and closer to opposition, which means that those planets from our perspective are going to be on the opposite side of the sun. That's also the closest approach that Earth will make um, to those planets for the next year or so, because of course Earth is going around the sun once a year. So, but once those are past opposition, they will of course be in the evening sky, because that's another definition, is that uh, objects are at opposition uh, uh, means that those objects rise when the sun sets. So they're exactly opposite. So that's what's going to happen. And as the days and weeks and months go by, they will be in the evening sky. Well, Venus is going to be in the evening sky as well. Mercury is sort of, I think, already starting to dip towards the sun again. So, we might have to wait another 88 days, another 3 months, um, for Mercury to be visible. But pretty sure in 3 months, pretty sure that Venus is still going to be out in the evening, and of course, Mars, Jupiter, and Saturn are going to be visible in the evening. So I'm predicting that, let's see, March 21st, April, May, June, somewhere, interesting, somewhere around the solstice, somewhere around the solstice, we're going to be able to see all 5 visible planets, and technically speaking, you can add a six, because in order to see Earth, you just, sort of have to look down. So all 6 visible planets in the same basic sky, um, right around the solstice. Interesting. Gonna have to check that out. Make sure you note that you heard that first, right here, and you know um, be ahead of the crowd a little bit and watch this show, because I think that's sort of what it's about too, is sort of looking forward and looking at the bleeding edge. And yeah, so when everybody's excited about this in June, um, I'll just sort of be like, well, yeah, is that new news? I mean, technically speaking, we can predict orbits for thousands and thousands of years. So is it that big of a deal? Whoop! I went the wrong way with that. There we go. Whoop! All right. Well, cool. So just a quick update on my um, preliminary project to characterize this telescope you see behind me. This is a Celestron Nexstar 8 SE. So it's an 8-inch telescope, has a primary mirror back here, big mirror that's got a hole in the middle of it. And this mirror is curved. It's concave, right? So it's kind of hard to show, but yeah, it's concave. So the light comes in this way, goes through the whole telescope, reflects off of this concave mirror, that reflects it onto a secondary mirror that's up here, and then that secondary mirror is convex. It's actually curved the other way, and that reflects the light down through that hole into or through the eyepiece. And you can either put an eyepiece here, or you can put a camera there, whatever you prefer. And yeah, so that's basically how that works. What I'm doing is I'm trying to see how well this system can do astrometry, which is the measure of the positions of targets in the sky, and how well it can do photometry, which is the measure of brightnesses of targets in the sky. And the astrometry is really, really easy, relatively speaking, and actually very, very, very good on this scope. I'm getting subpixel accuracy and precision, about a third of an arc second um, accuracy and precision. So that's very, very awesome. I'm really, really pleased with that. Um, and that's actually doing astrometry. Well, not necessarily in a crude way, but relatively crude. There are some ways that I might be able to tighten up those numbers, especially the precision. The accuracy, I think you know, I'm limited in that um, my pixels are about 1 arc second in size. So to expect to be able to measure anything better than third or a half of a pixel, that's about as good as I can expect. But I'm pretty happy with that. That's a-okay. That meets my requirements. For another project that I'm hoping we could be able to start here soon. What's holding me up is the photometry. Now, photometry is a lot harder um, because you have to measure the brightnesses of these targets, and also with um, high accuracy and high precision. And in order to do that, you have to make sure that the data is calibrated. You have to take all the systematic effects out of your raw data. So just the information from um, the target, be it a star, a galaxy, whatever. Um, so just the light from that target is being measured. And what I found recently is that um, you know it's astonishingly good, um, given the data that I have. The data that I have is pretty low signal to noise, uh, and overall, very very low signal. A 2-second exposure um, with a uh, of a 10th magnitude star um, gives me a count, a value of of uh, of roughly about 400 counts. Um, Now I've got a dynamic range on my camera of 65,535 counts. So a 10th magnitude star isn't isn't even quite hitting the 1% level in terms of my dynamic range. So mm, it's really, really hard to do good photometry with those kinds of levels. The numbers are just too small. The signal to noise is is just too low. So uh, signal to noise is just that. It's a ratio between sort of your peak signal and uh, and the inherent noise in in these systems. Noise comes from all kinds of places. There's not much that you can do about it except try to minimize it. So, and if you can't minimize it, then you try to characterize it. So at least you have an idea of what it is and all that. And really, we want a signal to noise of as high as we can, 100 to 1, 1,000 to 1, million to 1. Um, what I'm getting, I don't can't say as I've actually measured the signal to noise of my guys yet, but I'm saying that a 10th magnitude star is looking like it has a signal to noise of about maybe 5 or 10 or so. So it's not a lot to be able to grab onto and do very very accurate photometry, measuring the brightness of of these things. Um, so what I have to do is I have to find a way to boost the signal. Have to boost the signal, and the only way to do that is to somehow make a longer exposure. So instead of a 2-second exposure, I would like to do a 10-second exposure or a 10-minute exposure. Um, Problem I have with doing that at the moment is that while this telescope does track the sky, it doesn't track it uh, that well. So it um, it'll track relatively okay, but it won't track, um, to the pixel, right? So what I see, um, if I were to take, like a minute exposure, right? I would see all the stars in the field just sort of drifting around, and it's not exactly random, but it isn't linear either. So it wiggles around, does this. Sometimes it has sort of a general motion, but it'll wiggle like this, and it'll do this, and it'll go backwards, and all of that. So my tracking isn't really all that great. So I'm sort of limited in exposure time to maybe 2 or 3 seconds or so. Well, as I'm finding out, that doesn't do well for photometry. I just can't get the kind of accuracy that I want. I'm getting an accuracy of about a third of a magnitude, a third or a fourth of a magnitude. Sometimes better. Sometimes I'm getting an accuracy of around a tenth. It depends on the brightness of the star. It depends on the signal to noise. So the fainter stars, I'm really not making very good measurements there at all. I'm really impressed by the precision I'm getting. So in terms of repeatability, like I can take 20 2-second exposures of the same um, field of view. I've been looking at two um, clusters of stars, M41 and M46, and because they're relatively bright stars, there's uh, quite a spread in brightness or magnitude. So it's a good way to sample and test systems. Uh, so I can make measurements of those, and I can do like 20 of them, and I can look at the same star in each image, and that's depending on how bright the star is, depending on the signal to noise. Um, those measurements are actually pretty consistent. I'm actually seeing um, best precision I'm getting right now is about 50 um, 50 millimagnitudes. So that's 0.05 magnitudes. So that ain't bad. And what that really tells me is that if I can somehow improve my signal to noise, especially my signal, um, then I think I'm gonna get kind of the results that I'm wanting. Now, what I want for sure is an accuracy and precision that is at least 1/10 of a magnitude or less. The smaller, the better. And I think my ticket to that nirvana is signal. Now, as I said, at the moment, I cannot track longer than about 2 or 3 seconds. So I've got two solutions. One's a short-term solution. The other is sort of a longer term solution. The longer term solution is to uh, is to get this thing called auto guiding running. And it turns out I thought a couple of weeks ago I thought that I had hit a brick wall there, and because I'm using some pretty old software to talk to my camera. Now my camera, okay, is an older camera as well, okay, but it has actually two CCDs on it. One is the imaging CCD. The other one is the auto guiding CCD. So the possibility of auto guiding is definitely there, is definitely there. But I had two what I thought were um, showstoppers. The first the first showstopper is that the software that I'm using will not talk to this telescope. It won't send the right kinds of signals out to be able to tell this telescope to correct its motion at all. And on top of that, I didn't think that there was any other software out there that could do that. Well, I put a question out to um, what's his name? Dylan O'Donnell? Is that it? Is it Dylan O'Donnell? I'm not going to remember now. Let's see if I can find him here. Definitely shout out to Dylan if that's his name. Let's see. Let's do it this way. This might give me an alphabetical list. Oh no, that's just that. Okay, let me go to my history because I was just watching him the other day. So he's going to be up here somewhere. Relatively not long ago. Dun, dun, dun. Wow, where is he? There he is. Yes, Dylan O'Donnell. So check him out on YouTube. He's he does primarily, it looks like, astrophotography. So he knows about auto guiding, and he pointed out a piece of software that he said, well, why don't you try this? Well, it turns out, I looked at the specifications. It turns out that that piece of software, which I'm not remembering what it's called now. Let me see if I can find that as well. I think I saved a link to it. Did I not? I did not. Bummer. Um, anyway, he's got a great YouTube channel. Definitely check him out, Dylan O'Donnell. Great, awesome. Um, well, it turns out that that piece of software does and can apparently uh, talk to this telescope mount, and so there's a possibility that I am going to be able to auto guide, do some longer exposures, some very long exposures, pretty much as long as I want. Um, and so, yeah, we'll see how that all goes. It's not entirely necessary because the other thing I can do is I can actually take a series of short exposures and add them up, and we get you get exactly the same result. Um, if you were to do 10 2-second exposures, that's the same as a single 20-second exposure. Exactly the same. So so yeah, I don't necessarily have to track for minutes or hours. I can just take a lot of exposures and add them up. The only complication with that, of course, there's always complications. The only complication with that is that because of this telescope mount, which is called an altitude azimuth mount, it uh, when I make an observation, create an image like a 2-second exposure, um, the because this is an alt-az mount, um, it introduces a um, uh, curvature in the field of view, and and uh, and so the only way around that is to either limit yourself to these 2-second exposures and forget about it, or you can actually take that data and rotate it slightly and then add. So that's what I'm in the process of doing now. Um, it's it's always a toss up, whether you use sort of an established piece of software to do your work or sort of do it from scratch. And if I haven't done something in a while and I sort of need to get myself refreshed on what the process is and all that, I'll start from scratch. And so that's what I've done in this case. So I've started um, uh, writing this code. Whoop, go up. Writing the software to um, not only shift and add these images, because as I said, the tracking makes all the stars wander around. So I have to be able to register those all those stars, and it's not only just a shifting, but it's also a rotation. So I have to be able to shift and rotate, and then add them all up. And the hope is, and this is based on knowing that this kind of thing works. Um, the hope is that the signal will be boosted by a significant amount, and just doing a very 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 crude, just a shift and add on a couple of the stars in that field of view. I went, yeah, 20 images. Um, if they're all around, 400 or 500 each, then when I add them up, I'm getting around 8, 9, 10,000. Okay, which is still, only 15% of the dynamic range of the camera, but it's better. It's better than 1% of the dynamic range. So I'm hoping with some more signal that my accuracy will be improved. Um, I'll just I'll just have to collect much more data. So so what? I mean, what are these machines for? I mean, that's what they're for. So yeah, um, uh, that's not a problem. Not a problem at all. It's just time, and I have time. I try to have lots and lots and lots of time so I can do these kinds of things. So no problem. Cheers. So that's where that is. I'm almost finished with the rotation code. It's giving me a couple of headaches just because it's been so long since I've had to think about this. I'm having to do subpixel shifting, and so it's just it's it's not really a nightmare, but it's you have to think in in weird ways, um, not not sort of the normal way. And so, yeah, these kinds of things um, take a little while, but I actually thoroughly enjoy the challenge and you know being frustrated and um, you know like really pissed off that this thing just doesn't work right and all of that. It's part of the process, and deep down I thoroughly enjoy all of that. So not a problem at all. um, and as I said, I could have probably found, in fact I know that I can find software to do the rotations for me, but this is kind of a specialized thing where I wanted like an all-in-one package. So I want it to be able to grab an image, find find a couple of reference stars, figure out how much it has to shift, how much it has to rotate on a sub-pixel basis. Um, fractions of a pixel. I can do hundredth of a pixel, a thousandth of a pixel. It doesn't matter. Um, uh, but I want to be able to do all of that and then add them up. And I sort of want that to be all in one package. And that's I mean I've already got it all worked out in my head. So it's just a matter of filling in all the details and getting the code to actually work work right. Rotation is really, really easy. Um, there's just a couple of little subtleties that no one seems seems to talk about when, well, like especially when um, you're doing subpixel stuff, because it's sort of a different world out there. So, all right, cool. Enough of that. Hopefully, that'll be up and running in the next day or two, and I'll be able to present you with some results. And then I'm going to want more data. Astronomers and scientists in general always want more data. And if this is the technique that I have to use, then I need to collect a lot more data, um, more images that I can, shift and rotate and add in order to get the signal up. And then we'll do a photometric evaluation again, where I'll make measurements of the brightnesses of stars, and I'll compare those brightnesses to the measured brightnesses in a known and trusted catalog like Gaia. I've been using Gaia lately, um, uh, and hopefully those numbers will be very, very close, which means the accuracy will be very, very good, and hopefully also the consistency. Uh, you know, I make 20 um, measurements. How close are they to each other? So yeah, yeah, very cool. All right. Well, I posted a paper over on my Discord server about a white dwarf star, and I let's just look at that paper or so. White dwarf stars are, at least this is the story. Um, so white dwarf stars uh, are a type of star that is is like one of three or four end states of stars. So, uh, as the story goes, stars are formed in these large clouds of gas and dust, and due to perturbations and whatever else in these clouds, um, little regions begin to form where there's a little bit more stuff. And so the story goes, when there's more stuff, there's more gravity. So with more gravity, more things come in, it gets accumulated. Um, when there's enough mass, there's a lot of pressure in the centers of these bodies. The pressure builds, the temperature goes up, the pressure builds up, more mass, until temperature and the pressure is sufficient to supposedly squeeze hydrogen nuclei together to form helium nuclei, and that's what's called hydrogen fusion. And once that occurs, it's said that the star has turned on, and that's that's at, at that point it has some kind of mass, some kind of like initial mass, and according to the theories at least, it's the mass of these stars at that point when they turn on that sort of determines the rest of their lives. Now, if they're a star like our sun, like the mass of our sun, which of course is one solar mass, um, uh, this newly formed star will basically, burn hydrogen for most of its life. And when I say burn hydrogen, I mean fuse hydrogen. It's not burning in terms of you know um, oxidizing. It's actually fusing um, protons together to form helium. Um, so this can go on for billions of years, and in the case of our sun, it has been going on for several billion years, and will basically continue for several more. But eventually, the hydrogen burns out, runs out, and when that happens, of course, you know the outward pressure from from the fusion becomes less, and all that mass starts to push down and squeeze the star um, tighter. Well, that increases the pressure, which increases the temperature, and eventually the helium nuclei begin to fuse. That produces a lot of energy, and that will typically cause, at least as far as the story goes, the star to expand into what's called a red giant. And our sun supposedly is going to do this. It'll expand probably out to about the orbit of the Earth. So at that point, the Earth is toast. So make your plans now, because in 3, 4, 5 billion years, the Earth is well, will be no more. Will be no more for sure. At least according to all the models, right? And these are good guesses at this point. But being open-minded and skeptical about things, I'm not saying that this is how it is, but it seems like there's pretty good evidence um, for this kind of behavior, right? So so the helium fuses for a couple 100 million years, I think, until it starts to run out as well. So this is where the mass of these stars start to play a more significant role. So if we're talking about a star that's about the mass of our sun, okay, once the helium starts running out, the star will start to contract again, because it's not feeling that outward pressure from the helium fusion. It'll start to shrink again, and pressure will increase, temperature will increase, but it doesn't have enough mass. Um, yeah, it doesn't have enough mass to really do anything else. Now that fusion process of of helium nuclei produces primarily like carbon, oxygen, um, you know, those those sizes of atoms. You can get all kinds of other things too, and there usually is all kinds of things already in this star. But this is what the star is actually making, right? So uh, at that point, there isn't enough mass to produce enough pressure um, and temperature in the center of these stars to start fusing carbon and oxygen atoms together. There isn't enough um, um, energy to do that. So the star just shrinks. It just shrinks. Sometimes it'll shrink and sort of bounce back, produce a little shock wave, and we get something like the Ring Nebula, Messier 57, where sort of the outer atmosphere of that star has been blown off, and right in the center of this ring is a very very hot, dense uh, uh, core of a star, where the center is, carbon and oxygen, and the atmosphere is hydrogen, helium, sort of the lighter elements. So all the heavy stuff has sunk to the bottom. All the light stuff is on the top, um, and that's actually what we see when we look at the spectra of these stars. Is we see a lot of hydrogen and helium for for the most part. For the most part, now these are very very dense stars, so they have roughly the mass of our sun, but but they can be like the size of the Earth, right? Just incredibly dense. Usually pretty hot. Again, it sort of depends on their age, what their composition is, but they're going to be sitting around 10,000 degrees Kelvin, which is essentially 10,000 degrees Celsius. Um, they have pretty a pretty high gravity, sometimes 5 or 6 times that of the sun, just because of the density, right? It's just a very very uh, dense, intense, so-called gravitational field. They also usually have a very, very strong magnetic field on the order of like 10 to the ninth Gauss, a billion Gauss. Now, the magnetic field of the Earth, just as a comparison, is like a third or a half of a Gauss. So these stars are, a billion times stronger than that in terms of the magnetic field. And when we look at them, for the most part, they look very, very white, very white. So that's what we actually call them, are white dwarf stars. And yeah, as the story goes, these are, one of the three or four end states of stars. A star like an M dwarf, a very, very cool low mass star, probably is just going to burn out. It's just going to fade out, right? Um, Now, if you have a star that's like 1.4 times up to maybe 3 or 4 or 5 times the mass of our sun, um, these these collapses will sort of continue for a little while. The final collapse there is so intense that it actually squeezes the electrons into the nuclei of the remaining atoms to form neutrons. Just basically a solid neutron mass. So this is taking the 2 or 3 or 4 times the mass of our sun and squeezing it down to a neutron star that's maybe 10 or 100 kilometers in size. So city size or state size. Just insanely dense. At least this is the story, right? Um, just insanely dense. Most of these objects rotate, and of course they're very energetic, and so what what we oftentimes see is these neutron stars blinking, either in radio light or visible light, infrared light, um, maybe all wavelengths, maybe just certain ones. Um, Sometimes the period can change. It's just all kinds of things, and of course we call those pulsars. So pulsars are just rotating neutron stars that are emitting this light in sort of a periodic way. And those periods are usually pretty fast. I think the neutron star um, in the center of the Crab Nebula, I think that's pulsing at about 30 times a second or so. It's definitely not the fastest. It's definitely not the slowest. I've heard some pulsars are, you know, uh, millisecond. I don't want to say microsecond, but they're very, very fast pulses. And of course, the final end state of very, very massive stars, supposedly, never actually seen this happen, never actually seen any of these things yet, but very, very massive stars could, at least according to the math, according to the models, as I said, no observations of this have actually been made, but could turn into a black hole. So sometimes these white dwarfs, when their core collapses, um, that's sometimes can be a very energetic event. Um, Primarily because what happens is a lot of times these white dwarf stars are the companion stars to a more massive star, or just some kind of a companion star. And if their orbits are situated in such a way, there can actually be mass transfer between the companion star and the white dwarf. Now, if enough mass is accumulated on the white dwarf to exceed this limit of about 1.4 solar masses, then the star can actually move into that next phase and get extremely energetic. It can actually explode into what's called a type 1A supernova. And these kinds of things have been observed, and they can look at the progenitors, the white dwarf before it explodes, and then after it explodes, and it's like, yeah, that was definitely a white dwarf, and it had these characteristics and all that. Um, uh, so yeah, sometimes that can happen. This particular white dwarf that I'm looking at the paper of here is sort of an unusual white dwarf in at least a couple of different ways. First is that it's moving very, very, very quickly. And let's pull up the paper here. This is archive.org. If you want to keep abreast of the bleeding edge of um, um, not not only astronomical topics, but a lot of different sciences, math, economics, computer science. This is the sort of the bleeding edge um, in terms of what's going on in these areas. And archive.org is updated every single weekday, um, usually around like 1 hour UTC or so. So right after the beginning of the day, uh, they will update it, with the latest and greatest papers uh, that have been accepted for publication, but haven't actually been published yet. But as soon as they're accepted, they can be thrown up here as what's called a preprint, and we can go and grab them. So so this white dwarf, I guess they have identified it as an actual white dwarf star, is not only moving incredibly fast, but it also doesn't have sort of the characteristic elements that white dwarfs have, like hydrogen and helium and sort of the lighter elements. These guys are seeing all kinds of shit that sort of surprising, sort of cool. Let's see. So there's a low resolution spectrum of sort of a typical white dwarf star. So this is going from what, about 3,500 angstroms up to 7,000 angstroms, and you can see all these absorption features, all of these darker features in here. Well, believe it or not, I dare say that every single wiggle in here corresponds to some kind of an element uh, that they've accounted for. So, when you have absorption like this, that means that whatever that is there. Um, so that's pretty cool. They did spectroscopy, they did photometry. So they looked at the light coming from this object. They spread it out into a spectrum so they could try to determine, what this star is made out of. They did photometry on it. Again, just measuring the brightness of this thing. So let's see if we can look at some pretty decent spectra here. Oh, here we go. So I believe that this top red line is a model spectrum. So they can say, okay, we're going to throw in some sodium, we're going to throw in some silicon, we're going to throw in some magnesium, uh, all that. Let's throw it into our model and see what kind of star we can make. And we can make a particular star, and then we can take its spectrum, and we can see all these absorption lines in here. So this is sort of the model spectrum, and this is the actual spectrum that was collected at the telescope. And as you can see, can I zoom in here? You can see that they're actually identifying quite a few elements, right? You can see there's a little absorption thing here where there's a gap that they're calling magnesium. Oh, I've got a kitty. I've got a kitty who wants me to play doorman. Okay, I'll be right back. Take a look at this spectrum here. Hold on. So yeah, they're identifying magnesium, aluminum, calcium. Here's a here's a really dark absorption line. Magnesium, calcium, manganese, silicon, oxygen. It's amazing. Oxygen, all of that. Yeah, very cool. I was going to say something about this, and man, it just flew out of my head. What was I going to say about this spectrum? I don't remember now. It's horrible. But yeah, practically every single little wiggle on here has, you know, has some kind of um, identification. Now they can identify all these lines because they can go into the laboratory and um, they can um, uh, take a look at like a glowing cloud of magnesium one. Okay, they can look at a glowing cloud of that, and they can see that those features exist at, at those wavelengths. What wavelength is this? This is about like what is this? That's I don't think that's zero. That's about 3,000, 3,000, 4,000. So yeah, maybe about like 3,800 angstroms or so. Um, uh, you should see a very, very broad and deep magnesium 1 absorption line. And they see that in the lab, and they look up at the sky and they see the same absorption line, and they say, ought to be the same thing, right? Makes sense. Makes sense. But they're very complicated. As you can see, there's a lot of information here. It's amazing how much information is in spectra. Not only can you get photometric information from a spectrum, but the, the, the depth of these features tells you something about how much stuff there is of that element. The width, the width of these features tells you about the magnetic field, the temperature, um, and then of course all these absorption lines tell you things about what the star is made of. Now, white dwarfs, as I said, typically are hydrogen, helium. That's about it. But in this case, this white dwarf star has all this other stuff in it. Isn't that amazing? White dwarfs are pretty amazing stars. Just gotta say. So yeah, I think this is these are just sort of zoomed in areas, right? Because this is going from 46 to 54. So that's just this little area right here. And then this is going from 82 to 9,000. So that's just sort of up, up here, right? And so, yeah, they're seeing titanium, aluminum. Here's iron. Here's some iron lines. Iron lines over here, supposedly. Ooh, I don't really see much there, but hey, who am I to argue, right? Let's see if there's any other interesting pictures, since I noticed we are already over the hour. It's amazing how time flies. Just more pictures of spectra, trying to, it looks like they're trying to understand. Yeah, that's another piece of information that you can extract from spectra. You can actually measure the motions of these objects as well, or even the motions of things in the objects or on the objects. So yeah, it's just absolutely amazing what kind of information you can get from a spectrum. I would definitely, uh, I'm definitely interested in outfitting my telescope with a spectroscope at some point, because yeah, so much. I mean, really, really, if when it comes down to it, if you want to do the real scientific work um, with astronomy, you have to have spectra because there's so much there. It's just absolutely amazing. But anyway, so they're just measuring the locations of these absorption features, and um, I don't know. Do they say? Let's see, bottom. So they're using synthetic spectra here, comparing it to the actual spectra. That's okay. Seeing silicon and aluminum. Yeah, pretty awesome. It's a very unusual white dwarf. So they really they don't really have an idea. They've got some speculation here at the end in terms of what they think it's why it looks like it's made up of what it's made of. Here are some measurements of its speed, and as you can see, it's clipping along. 500 kilometers per second is pretty consistent there, pretty consistent. So that's moving. That's moving pretty fast. But I guess the speculation right now, we can actually go down to that. Um, let's see. Where does it say? Do we have? We conclude that the interpretation of LP 40-365 is still subject to some uncertainties in the spectral analysis, which will eventually be solved in future follow up observations. Um, near ultraviolet. See, I thought that one of our best fit. Where does it say? I thought we were talking about. Yeah, so um, what they're speculating um, is that this is some kind of a failed supernova explosion core, where you know, as I said, a Type 1a supernova is when a white dwarf is orbiting another star and mass is being accumulated until enough mass happens that it explodes into a supernova. And what they're speculating here is that something sort of went wrong with that, so it was able to keep a lot of its um, material, um, and maybe not really explode, but just sort of go and be shot out. So yeah, there's a lot of uncertainty in terms of what the star is doing. The fact of the matter is that it's there. It's moving very very fast. It's made of very very unusual um, elements that are not typical for white dwarfs. But I guess, and we'd have to look at the references to really find out uh, how it was determined that this is a white dwarf. But let's um, go with the idea that it actually is. Well, if it's a white dwarf, why are we seeing titanium and silicon and magnesium and all that? Well, as the paper says, maybe it's because it's some kind of a failed um, supernova 1A explosion. Um, but something has also propelled it into this, hyper velocity. So yeah, really don't know. It's a mystery, but I don't know about you, but I like mysteries, especially scientific ones that just baffle and boggle the mind. Yeah, I like it. You know, if we understood everything, it'd be boring. So let's keep the mysteries coming, and I'm gonna get out of here for now. I'm gonna get back to code writing, try to get this rotation stuff done. And all right, and uh, my voice is just absolutely going tonight. So yeah, I'm gonna get out of here for now. Um, yep. I'm being called back up to the ship. So glad you could stop by. Talked about white dwarfs for a little while. A weird one, pretty weird one. Um, but yeah, check out archive.org for all the latest and greatest bleeding edge astronomical research. And yeah, all right, I'm going to get out of here for now. I will see you on the spin in less than 23. All right. Cheers and peace. Have a great night and a great day tomorrow. Bye.